Good morning, teacher. My name is Nguyễn Phi Long, and my student ID is 23110037. And today, I would like to present the lab number 6 of the Networking Essentials course to you. As you can see here, the lab number 6 is called Inspecting the TCP Protocol. And in this lab, I will investigate the TCP protocol, how to use the T-short, also the Docker, and I will examine what is the three-way handshake is, and how a client interact with the server. First, I have created an environment for this lab. The terminal number 1 represents for the client. The terminal number 2 represent for the web server. And first I will use this instruction for the client to listen here, and then I will use this link for the web server. This is the information of the web server. As you can see here, there are 12 packets received by a filter, and if we want to see the list of these packets, we will use this instruction. This is the 12 packets, and we will go to the question number 1. We will identify the three-way handshake of this connection. First, what is the three-way handshake? Here, the handshake protocol consists of 3 steps: 1, 2, and 3. Step 1. The client sends a SYN-X packet to the server with the randomly generated value X called the sequence number. Step 2. After the server receives the SYN packet from the client, it will reply with a SYN-E plus ASCII X plus 1 packet, in which E is the random value generated from the server, and the value X plus 1 of the ASCII packet is the acknowledgement packet for the SYN packet with the random value X received from the client. And step number 3, the client receives the packet from the server and sends back an ACK acknowledgement packet to the server. The server receives it and completes in the 3-step handshake process. A transmission channel is established between the client and the server, and now the process is begin. And here we can see this the SYN, the first 3 packets, 1, 2, and 3. Here is the first step, the SYN, and the next step is SYN-X acknowledgement, and the third is acknowledgement. Also, the final step of three-way handshake, as I explained before. So we can conclude that this is the whole process of the three-way handshake. We go to question number 2. What are the IP address and TCP port number? We will look at the packet number 1. This is the my IP of my computer, which has the port of 55208. Beside that, the port 18 represents for the HTTP Hypertext Transfer Protocol. We will move to the third question. Identify the HTTP request replies. We will come back to this. Now we will look at packet number 4. We can see the get here. So the client, which is my computer, sends an HTTP get request to retrieve a result from the web server here. And after that, when we look at the packet number 6 here, we can see that is a 200 OK, means the web server acknowledges the request and starts sending back the request resource. The server continues sending their data. And the packet number 8, we can also see here is the 200 OK text HTML. This packet indicates that the server is transmitting the actual web page content in text or HTML format. And we will look at the packet number 9. In the packet number 9, the client acknowledges the receipt of the response from the server to conclude that the request for data is initiated by the client via an HTTP GET request in the packet number 4 here. And then the data retrieval from the web server happens in packet number 6 and number 8, where the server sends an HTTP 200 OK response along with the requested content. The client successfully retrieves the data and acknowledges it. We will go to the next question. Is we will identify the TCP disconnecting sequence. Okay, now so we will have to know what is the TCP disconnection first. As we know, the three-way handshake is the started. So what is the finish? The finish is the four-way handshake. Now, what is the four-way handshake? We will look at this picture. There are 4 steps. Step number 1, initiator sends the finish to close the connection and send a fin packet to the receiver or the server. This packet indicates the end of data transmission from the initiator to the receiver. And the step number 2 here, the receiver sends ACK. The receiver receives the fin packet and replies with an ACK packet. It acknowledges the reception of the fin from the initiator, but does not terminate the connection from the receiver side. Step number 3, after receiver has finished transmitting any remaining data, it sends a fin packet to the initiator indicating that it's ready to close the connection. And the initiator receives the feed from the receiver and responds with an ACK packet acknowledging the termination request. The initiator then enters the time wait state. Here is the time wait state, waiting for a certain period to ensure that the receiver has received the ACK. After this period, the initiator fully closes the connection. Close, absolutely. But we will look at it. We will see what happened. We will look at the last 3 packets from 10 to 12. We only see there are 3 steps. But why? Why is there only 3 steps instead of 4? Because in an optimized TCP teardown, a host can combine the second and the third step. In the packet 11, we can see that there is the combination in this packet. print an ACK here. So we will, so in conclusion, the packet from 10 to 12 is the disconnecting. So we will move to the next question. Is view TCP conversation. To view the TCP conversation, I will use this instruction. As you can see, here is the TCP conversation. So this is the TCP conversation. I have made it the full screen for you to look more easier. As you can see here, the client, which is me. The port is 55208. Send 5 packets, 5 frames, which has 962 bytes to the server, and then the server, which has the port 18, represent for HTTP containing 547 bytes. The entire conversation consists of 12 packets, which equal 5 plus 7 and 1509 bytes of data exchange. The relative start here. This is the timestamp when the TCP conversation began, and the duration for is the entire TCP session lasts. So the conclusion is the client is me send an HTTP request to the web server, and then the server responds with less data than the client server, indicating a small response, like an HTTP GET request receiving a short reply. The entire exchange was completed very quickly here. Going to the next question, we will use the follow TCP stream. At first, we will use with ASCII output here. I will use this instruction. And here is the ASCII. This command is used to display the entire TCP stream between two IP addresses from the file input pcap in ASCII format. So we will figure out. First, the node 0. Here, this is the client. Is my machine sending a request from port 55208, and the node 1 here is the server, web server, receiving the request through port 80 HTTP. And here is the HTTP request. The get HTTP 1.1 request to retrieve the entire page from the server using the get method of HTTP. The host, the server IP address. Here is the server IP address. User agent. This is the client is using the curl tool to span the request. Accept. Here it means the client accepts all types of response formats from the server. Next, HTTP 1.0 200 OK. This means the server returns a status code 200 OK, indicating that the request was successfully processed. processes the server. Symbol HTTP here. It means the server is running using the Python symbol HTTP server and contain type text HTML. The response is an HTML page. The size of the response content is 438 bytes. Last modify is the last modification time of the HTML page. The TMT time. Finally, the HTML content here. This is the basic HTML page displaying the message. Hey, this site is healthy. Feel free to play with it. So overall, this command shows the entire request-response process of HTTP between the client and the server, running on Python symbol HTTP server. The HTML content of the page is fully displayed in ASCII section of the command. We will just go through the ASCII output. Now we will find out what is the hex output. I have used this command to find out what's the hex output here, and you can see that as you can know, the hex is much longer than ASCII, so we'll find out. In here, it also has two dots similar to the other. Dot 0 is my computer, is the client. The dot 1 is the web server. And in here, we will see that the left side, here is the left, is the hexadecimal data. The right side here, the right side here is the ASCII representation if the data is printable. Otherwise, it will represent by a dot like this. Each line begins with an offset number. Here is some offset number indicating the byte position in the stream. And so what the stream contains here is the HTTP request, get HTTP 1.1 host user agent. Like in the ASCII output, this indicates the client is making the symbol HTTP request to the server using URL. So the HTTP response, the server reply with an HTTP response. It's just similar to the ASCII output, but now it has the hex here over here. And finally, it also has the HTML content decode to plain text from hex. After go through the following TCP stream, now we will continue to review detailed TCP messages. Here, I will use this. Detailed messages. This is the detailed messages of frame, as you can see. Now we will figure out. First, we can see that this is the frame information. This is the 4th packet captured in the PCAP file. the byte on Y. Here, this is the byte on Y. We have 143 bytes. It means 1144 bits. The size, this is the size of the packet on Y. I capture also equal the byte on Y. Here, the interesting in here is that you can see the every protocol in frame. This is contain the layer Ethernet, IPv4, TCP, and HTTP. We move to the Ethernet. This is the data link layer. You see that the short MAC address, the destination, also the destination MAC address. These MAC addresses are locally administered address, not factory default addresses from the manufacturer. We will continue to the network layer. Here, IPv4, Internet Protocol version 4. The short IP is the client. Here is my computer. And the destination is the web server. This is the version number 4. And the header link is 20 bytes. The total length is 129 bytes. Here we can see that the TCP protocol is number 6. It's really similar to our last lab that we have did. It's the lab number 5. Finally, is the TCP. This is the transport layer. We see that this is a source port, destination port represent for HTTP, and finally this is the HTTP represent for the application layer. Here, so we have been go through detail every protocol in this frame. Now we will come to the last question of this part. Here is the view detail of particular frames by frame number. So I will choose here the frame number 5. Here is the frame number 5. It also has the same component. Frame number 4. Let me find with number 5. Here is frame number 5. Oh, this don't have the HTTP protocol. Why? Because let me figure it out. We will use this one to see the list packet again, and I will explain. Here, when you look at number 5, you will see that the length equals 0. That means that this frame doesn't have a payload. So that means it cannot have the HTTP protocol. It only have frame information here, like we analyzed in the first frame number 5, the Ethernet, net. IPv4, IPv4, the TCP. Here is the TCP. And now we will move to the 4.2 inspect along TCP stream. Now we will start. First, I will use this instruction again for the terminal 1. And then, as you can see here, we will have to use this curve for capturing packets. For terminal 2, as you can see, there are 30 packets received by filter, and we want to see the list. We only have to do this. This is the total list packet from 1 to 13, and you can see there's something special here. This number 2, the TCP out of order. So we will move to the question number 1. Now number 2, how many TCP segments have been retrieved? The length in byte. So I will combine the question number 2 and the question number 6 together to figure it out. For the conversation, I only have to use this. Here is the conversation. There are 13 frames, 13 packets from 1 to 13, and including 1 packet out of order here. The length is the sum of those numbers combined together, as I calculated here, is equal 6,299. It's also correct with this 6,299. That's why I combine 2 questions together to prove that I was right. And this is also the byte length of total 13 packets. And from the conversation, I can see that the client here using the temporary port 33338 to establish the connection, and it is the web server. 80 is the HTTP running on the default HTTP port. Here, the client sent 5 packets with a total 5,659 bytes to the server, and the server responds with a packet containing 640 bytes. The entire conversation consists of 30 packets here and 6,299 bytes of data exchange. The relative stuff here is the timestamp when the TCP conversation begins, and the duration is the entire TCP session lasts. Now we are coming back to the number 3. Identify the TCP segment. So what is the TCP segment? How to identify is the TCP segment? We can see that the source port, destination port, sequence number, acknowledgement number. We'll come back to here and see the packet number 1. So what's the 0.0000 here? Is the time since the packet capture start 0 seconds, mean this the first packet, and then no, this is the source IP address, the client, also my computer, and it's sending to the destination IP address is the server. This is the protocol TCP, and 74 is the total size of the packet, 74 bytes. This is the short port, the desk port, synchronize. Here is the connection initiation packet. It requests the establishment of a TCP connection from the client to the server, and some information behind here. Next, we'll move to the use the follow TCP stream. First, I will use the ASCII output. As you can see, it's really long because it's much more longer than in the 4.1. ASCII. As I said before, this the node 0 stand for the client, and node 1 represent for the server. This is the HTTP request, and then this is the HTTP response, like we do in the 4.1. And this is the HTML content of the web page. It's really long here. This is the basic HTML page displaying this. So we will move to the hex output. As you can see, if in ASCII it's much more longer, and then what happened in hex is even long here. Like we analyzed before, on the left side is the hex, and on the right side is the ASCII represent. We also have two nodes here, client, server. If the data is printable, otherwise it will represent by a dot like this. It's really long. Now we will move to the identify the no, we have already do the BTCP conversation, and now we will identify the TCP disconnecting frames sequence. we will use this to see the list again one more time. As you can see, the last three packets from 11 to 13. This is the four-way handshake has been combined into three steps in here. Finished ACK acknowledgement like we did. Finally, in this we will view detailed TCP message. This is the detail of the TCP message. We will find out. It's really long. It takes so much time to find. Oh, here we can see that it had a HTTP, TCP, IP, entity. First, the frame information, the Ethernet, IPv4 and IPv4, the TCP, and the most important is the HTTP. So we will move to the 4.3. Inspect a very long TCP string. Maybe perhaps much more longer than this. So now we are going to start now. I will use this again. And from the terminal 2, I will use this link LABSIX. Wow, it's absolutely the longest I've ever seen here. We can see that it costs 33 packets received by feeder. It's much more longer even. It's a much more packet than. Now we will find out the list of TCP packet. This is the 33 packet of this. Now we will go to the question. First question: how many TCP segments have been retrieved on the client container? The length in bytes, so we have to calculate it. As you can see, this has 33 packets and one packet out of order here. The length in byte, I guess it must be large because similar. Here, length in byte is the sum of it right here. I have calculated it, and this equal the total length is approximately 154 kilobit, 154 kilobit here. So I will combine this question like I used before to prove that the total length I was calculated is right. I will use this command to see the conversation here. As you can see, the total length is 100. 54 kilobyte here. Really large, and it's absolutely right with my results. We come back to the next question here. Now we will use the following TCP stream, including the ASCII output and the hex output. First, we use the ASCII output here to find out. I guess it must be long. Oh, it's the whole story. Now we will figure it out. Oh, it's quite long, so it takes so much time to find where the stream information. Where is the stream information? Oh, here. This the stream information. The node here is client port 36478, and here is the server port HTTP 18. This is the HTTP request and HTTP response is here. It's HTTP response, and the whole ASCII here is the HTML content of the web page. Oh, it's much longer than I thought. Oh, we use this for scrolling faster, and this is the whole story and the whole ASCII that we have to find out. And next we'll find out in the hex. Well, I guess it could be about longer, about triple more than the in ASCII. Well, let's see how much longer. Wow, yes, you can see here it's the long distance from the hex. So I guess that we don't have to scroll up there because it's just similar to the last hex that we have been analyzed. Here on the left side is the hex, on the right side is the ASCII. It's so long that I can't scroll over. And then we will identify the TCP disconnecting frame C1. So I will do this to see the list of the TCP packet. 33 packet. Oh. Now when we look at the last 3 packet here, you can see that this is the 4-way handshake. This means it's the disconnecting sequence. But if you look here, you see that is the combination like the other exercise. So it has only 3 steps here. And then now we'll move to the last content of this lab is inspect HTTPS TCP stream. I will go to the YouTube here. YouTube here. It has the HTTPS. So you move back to this use the TCP dump for the terminal 1. For the terminal 2, we use the URL of the YouTube. Over here, as you can see, it's very long because it's a huge pace of technology. Here is at 642 packets received by the filter. Now if we want to see what are the TCP port numbers, we will have to see the conversation. Now I will find out the conversation of this. As you can see, this is the conversation. As this web is a huge website. It's an HTTPS, so the total length is 658 kilobytes. This is the IP source, IP address, the client, and the port is 41730, and this is the server. Here 443 represent for HTTPS and 80 is represent for HTTP. This could be conversation. The client using temporary here to establish the connection. This is the web server running on the default HTTPS port 443. As you can see that the client sent about 449 frames. It's a huge frame, and the server respond with 193 frames. The total is 642 frames. The duration, the entire TCP section lasts a much more huge time because it had to deal with a lot of frame here. Now we will move to the last question. Can you tell about the communication sequence between client and server in the HTTPS? Here HTTPS is HTTP secure or HTTP over TLS over SSL is the secure version of HTTP. In terms of communication, HTTPS function similarly to HTTP, also using request, response, but the data is encrypted here using the TLS SSL protocol before transmission. Thanks to encryption, the information exchanged between the client and server via HTTPS here is secure, preventing it from being intercepted or modified by third parties during transmission. We can see that nowadays most people don't use HTTP anymore. They choose the HTTPS due to the security of it. Thank you for listening to my lab, and this is the end of my lab. Thank you very much.